At 1401 UTC on June 6, 2026, active region 4461, a magnetically unstable sunspot cluster located at coordinates S23E25 on the solar disk, released an M1 8 class solar flare. That classification sounds moderate. It is not the flare that should concern you. It is what the flare tore loose from the sun's surface as it fired. A dense, magnetized cloud of solar plasma, a coronal mass ejection now confirmed by multiple model runs to be traveling through interplanetary space at over 1-400 kilometers per second, aimed directly at Earth, with arrival predicted at this very hour on June 8, 2026. NOAA's Space Weather Prediction Center issued a G3, strong, geomagnetic storm watch for today. That watch is not a forecast of what might happen. It is a warning about what the instruments already show is on its way. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. When events like this are unfolding in real time, the difference between receiving that information now and receiving it after the fact is not a matter of convenience. It is a matter of preparation. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the European Space Agency's SOHO spacecraft, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us. But that is not even the complete picture, because what is arriving at Earth today is not a single event. It is the third significant solar salvo fired in less than 5 days from a solar region that scientists are now watching with serious attention. And underneath the question of what this particular CME will do to Earth's magnetosphere in the next 12 hours lies a far older and more consequential story. The story of what happens when a cloud of magnetized solar plasma finds the right orientation as it passes through Earth's magnetic field, when the conditions align not just for a light show at the poles, but for something the instruments of human civilization were never adequately built to survive. The question is not whether a solar storm can bring down a continental power grid. The question is not even a question anymore. It has already happened once. And the geological and historical record tells us clearly that what happened once was not the worst version of what is possible. To understand the weight of what is arriving today, you have to understand what 1,400 kilometers per second actually means when applied to a mass of charged solar plasma. 1,400 kilometers per second. For reference, the fastest bullet ever fired by a conventional weapon travels at approximately 7 kilometers per second. The CME is traveling 820 times faster than that. The distance from the Sun to Earth, 150 million kilometers, is a distance that light crosses in just over 8 minutes. This plasma cloud is not light, it is matter, and it is crossing that same distance in approximately 30 hours. What it carries when it arrives is not simply speed. It carries a magnetic field orientation embedded within it, and that orientation will determine everything about what happens when it encounters the magnetosphere that surrounds this planet. If the BIS component, of the southward pointing component of the interplanetary magnetic field, arrives pointed north, Earth's magnetic shield deflects the energy. The storm remains moderate, and the world wakes up on June 9th, mostly unchanged. If that BIS component arrives pointed south, the shield opens. Solar wind energy pours directly into the magnetosphere. Geomagnetically induced currents begin flowing through everything conductive on the surface of the Earth. Pipelines, railway tracks, submarine cables, and most significantly, the long-distance high-voltage transmission lines of the power grid. And at that point, the storm is no longer a space weather event. It becomes a civilization-level infrastructure event. The current confirmed activity sequence leading to this moment began on June 3rd, 2026. Active region 4455, carrying the highest possible magnetic complexity classification, a beta-gamma delta configuration, produced 3 significant flares in a single day, an M9, 3 at 0136 UTC, an M7, 7 at 07 UTC, and an X1. 0 class flare at 1128 UTC, confirmed by NOAA with R3, strong, radio blackout classification. That X10 flare caused a wide area blackout of high-frequency radio communications across the sunlit side of Earth for approximately 1 hour. Space weather physicist Dr. Tamitha Skov confirmed that the M9. 3-year event produced a direct Earth-directed CME stating publicly the solar storm launched during the M9. 3 flare is indeed Earth-directed. The subsequent CMEs from that same day merged in transit. What scientists call a cannibal CME, where a faster ejection overtakes a slower one, consuming it, combining their mass and magnetic energy into a single larger structure that arrived at Earth on June 5th, triggering G2 geomagnetic storm levels. Then, before that material had even fully cleared, active region 4461 fired the flare of June 6th, launching the 1,400 km per second cloud that is arriving now. Multiple model runs predict the CME's shock front reached Earth as early as 0.17 UTC on June 8th. The main body was forecast to arrive by approximately 06 UTC. What those models cannot tell you is the orientation of the magnetic field embedded in the core of that arriving plasma. That answer comes only from the ACE and DS-COVAR spacecraft, Sentinel satellites positioned at the L1 Lagrange point, approximately 1. 5 million kilometers sunward of Earth, and those spacecraft provide only 15 to 60 minutes of warning before the material reaches the magnetosphere. 15 minutes. In the context of grid management for a continent, 15 minutes is not a safety window. It is a final alarm. Here is where this account becomes genuinely significant. Because the scenario unfolding today is not a theoretical exercise in catastrophic possibility. It is a documented pattern. The Sun did this before, and when it did, the result was not measured in disrupted satellite signals or degraded GPS accuracy. It was measured in darkness. Millions of people, hours without power, a modern industrial grid reduced to its component failures in a time span shorter than it takes to drive across a city. March 13th, 1989. This is not ancient history. This is within the living memory of a substantial portion of the people watching this. On that morning, at 02:44 local time, the Hydro-Québec electricity transmission system collapsed. The entire provincial power grid, serving 6 million people, lost power in 90 seconds. 90 seconds. The cause was a coronal mass ejection that had struck Earth's magnetic field hours earlier, associated with a solar active region designated NOAA 5395, which had produced an X-15 class flare, one of the most powerful flares ever recorded in the era of satellite observation. The geomagnetic storm that followed reached a DEAST index of negative 589 nanoteslas, a measurement of the disruption inflicted on Earth's ring current, the belt of charged particles encircling the planet. For context, a DEAST of negative 50 nanoteslas is considered storm level. Negative 589 is in a category that the modern power grid, even with its upgrades, has never been forced to confront since. The CME's arrival drove a second CME shockwave at a transit speed of 1,220 kilometers per second, nearly identical to the speed of the cloud arriving today. That shockwave triggered a sudden commencement in the magnetosphere, sending geomagnetically induced currents surging through the buried bedrock of Precambrian igneous rock beneath Quebec. Rock that, because of its extremely low electrical conductivity, forces those storm currents to find an easier path. That easier path was the high-voltage transmission lines of Hydro-Québec. Transformers overheated. Circuit breakers tripped on cascade. Harmonic frequencies destabilized the system. In the time it takes to boil a kettle, one of the largest power grids on the continent ceased to exist as a functioning system. 6 million people woke to darkness and cold. The Montreal Metro did not run during the morning rush hour. Dorval Airport shut down. Schools, offices, hospitals on backup power. Hydro-Québec would spend an estimated $2 billion in the years that followed upgrading its systems, raising trip levels, installing series compensation, and hardening its monitoring infrastructure. The storm of March 1989 was later classified as a 1-in-50-year geomagnetic event. This is not a hypothesis. This is documented in the geological and infrastructure record. And the grid that was hardened against that storm was hardened to withstand, according to the best available engineering estimates, a 1-in-100-year event. That is a meaningful number. It is also a number that means, by definition, that an event exceeding it is possible. Picture the city of Montreal in the early hours of March 13th, 1989. More than 3 million people in the greater metropolitan area. Most of them asleep when the lights went out. The temperatures in Quebec in March average minus 8 degrees Celsius at night. When the heating system stopped, the cold did not wait for anyone to be notified. It began immediately. The people in those apartment buildings, the elderly, the families with young children, the people who had gone to bed the night before without any knowledge that a storm of ionized solar plasma was bearing down on the planet, they woke up in the dark, in the cold, in a city that had functionally ceased to operate because of something that had happened 150 million kilometers away 2 days earlier. Ask yourself, do those people know on the evening of March 12th what the data shows? Do they know that NOAA has issued alerts? Do they have 15 minutes of warning or 60 minutes or any meaningful window in which to prepare? They do not. The warning systems of 1989 were not what they are today. But even today, with the DS-COVAR satellite at L1, with the real-time KP index, with NOAA's Space Weather Prediction Center publishing alerts within minutes of new data, the grid does not respond in 15 minutes. The operators know the storm is arriving. The physics proceeds at its own schedule regardless. Now connect that history to the present. June 8th, 2026. The storm arriving today comes from a different region, AR4461, positioned at S23E25, but its speed is within the same range as the most damaging CME associated with the 1989 blackout. The incoming plasma's magnetic orientation is not yet confirmed as southward, and NOAA's current watch encompasses G1 to G3 conditions, with isolated G3, strong, possible. That is not AG5. It is not 1989. But here is what the data also shows. Active region 4456, which has been producing activity throughout the same period, now carries a beta gamma delta magnetic classification. The most complex configuration a sunspot group can achieve, the configuration most capable of producing the most energetic flares. That region has not yet fully discharged. It is still accumulating. And the system does not rest between events. The sun does not pause to allow the grid operators time to recover from the previous salvo before the next one arrives. This is the connected systems picture that makes space weather in 2026 genuinely different from space weather in 1989 in terms of consequence rather than just scale. In 1989, the infrastructure most vulnerable to geomagnetically induced currents was primarily high voltage transmission lines and certain types of transformers. Today, that list has expanded significantly. GPS-dependent timing systems underpin not just navigation, but the synchronization protocols of financial networks, cellular networks, and internet infrastructure. FR radio communications, disrupted by the R3 blackout from the June 3rd X1. Zero flare, remain critical for aviation over polar routes, for maritime communication, for emergency services in remote regions. Satellites in low Earth orbit experience increased atmospheric drag during geomagnetic storms because the heating of the upper atmosphere expands it outward. The GOES-18 satellite was experiencing an outage during the June 3rd event, requiring NOAA to switch to backup data from GOES-19 for X-ray classification, a detail that by itself illuminates the layered vulnerability of the monitoring infrastructure. The system watching the storm is itself affected by the storm. The instruments are not immune to what they are measuring. The oceanographic and ionospheric dimension of this event extends the story further. Geomagnetic storms produce heating of the ionosphere, the electrically charged upper layer of the atmosphere between approximately 60 and 1,000 kilometers altitude, that can alter the propagation of radio signals over thousands of kilometers. But they also affect the behavior of the equatorial electrojet, a current system flowing through the ionosphere along the magnetic equator, and by extension, influence GPS signal accuracy for every civilian and military system relying on it. In the Indian subcontract, where aurora visibility has been reported during the current active period, the ionospheric scintillation effects on satellite signals can render GPS accuracy unreliable for hours at a time. India TV News has confirmed that the current CME event may make auroras visible at latitudes, including parts of India, which is itself an indicator of the storm's reach well beyond the polar circles where geomagnetic disturbances are typically felt. Consider what that means for the approximately 4 billion people living across the Indian subcontinent. Navigation systems for commercial aviation, shipping lanes through the Indian Ocean, the agricultural applications, now dependent on GPS-guided systems in one of the world's most populated farming regions, all operating on infrastructure that is, at this moment, in the path of a cloud of solar plasma traveling at 1,400 kilometers per second. This is not about whether they will notice. Most will not. The disruption will be invisible to the majority of people experiencing it, but invisible disruption is not the same as absent disruption. The error accumulates in systems they trust, the timing offset in the network synchronization that no one monitors until it fails, the transformer that handles a surge at 03:00 in the morning when the grid load is at its lowest, and the geomagnetically induced current finds the path of least resistance. The failure that gets logged as unexplained because no one on the maintenance team thought to correlate it with the no AA alert that was published 11 hours earlier. The Carrington event of September 1859 is the reference point that space weather scientists return to when they want to establish the full outer boundary of what the sun can produce. On September 1st, 1859, British astronomers Richard Carrington and Richard Hodgson independently observed an intense white light solar flare, the first such event ever recorded by a human observer. 17 hours and 40 minutes later, the associated CME struck Earth's magnetosphere. 17 hours. For a CME to travel 150 million kilometers in 17 hours and 40 minutes, it must have been traveling at approximately 2,280 kilometers per second. The geomagnetic storm that followed drove a dist index estimated by modern researchers at negative 900 nanoteslas, exceeding the March 1989 event by more than 50%. Telegraph systems across North America and Europe failed, caught fire, and in some cases continued to operate without battery power because the geomagnetically induced currents were sufficient to drive the circuits directly. Operators reported receiving electrical shocks from their equipment. The auroras were visible as far south as Cuba, Hawaii, and Queensland, Australia. There were no power grids in 1859. There were no satellites. There were no fiber optic networks, no GPS constellations, no high-voltage transformers drawing current from a continent-spanning transmission infrastructure. The instruments of civilization in 1859 were not designed to fail catastrophically under geomagnetic stress. The instruments of civilization in 2026 are. A study commissioned by Lloyd's of London and the Atmospheric and Environmental Research Group in 2013 estimated that a Carrington-scale geomagnetic storm striking today could cause between 0, 6, and 2, $6 trillion in economic damage in the United States alone, with recovery times for the most severely affected regions measured not in weeks, but in years. The transformers most vulnerable to geomagnetically induced currents, the extra high voltage transformers that move power across continental distances, are not stored in warehouses. They are custom built. They weigh hundreds of tons. They are manufactured in a small number of facilities worldwide, and they require between 12 and 24 months to produce and install under normal supply chain conditions. A storm that damages dozens of them simultaneously does not create a repair timeline. It creates a replacement timeline. And during that replacement timeline, the question for the people living in the affected regions is not about inconvenience. It is about water treatment facilities, hospital backup power, food supply cold chains, and fuel distribution networks, all of which run on electricity. The monitoring is in place and detection is possible, but prediction is not. That sentence deserves to sit with the viewer for a moment before it continues. Detection is possible. DSCOVAR is at L1 right now, measuring the solar wind properties of the incoming material. NOAA's swpc is publishing updates. The KP index is being tracked. The BZAC component of the interplanetary magnetic field will be known within minutes of the CME's arrival at the magnetospheric boundary. Scientists are not blind to this event. They are watching it in real time with instruments they have built precisely for this purpose. But prediction, knowing in advance what the BZ orientation will be, knowing whether the storm will reach G3 or G4 or G5, knowing whether the next CME from the still active AR 40456 will arrive in 18 hours or 36 hours or not at all, that prediction remains beyond the current capability of the science. The models exist. The parameters are fed into them. The output carries uncertainty ranges measured not in decimal points, but in whole storm classifications. A storm that models suggest might reach G2 can reach G4. A storm forecast as G3 can arrive with a northward BZ and produce barely any coupling at all. The instruments are precise. The physics is complex, and the sun does not care about the distinction. Here is what the official data actually shows for June 8, 2026. Active region 4461 produced in M1. 8 flare confirmed by NOAA at 1401 UTC on June 6th. The event was associated with a filament eruption, a long, dark structure of magnetized plasma suspended above the solar surface that, when destabilized, launches material with both the filament's mass and its stored magnetic energy into interplanetary space. The resulting CME carries that magnetic complexity with it. NOAA's Space Weather Prediction Center published the G3 watch on June 6th at 22:15 UTC. EarthSky confirmed the CME's shock front arrival was expected by midday UTC on June 8th, with the main body following. The speed of that cloud, over 400 kilometers per second, places it in the same velocity range as the most damaging of the 1989 event's arrivals. The geomagnetic response depends on arrival time, speed, density, and magnetic orientation. 3 of those 4 variables are now known. The 4th will be known only when it is too late to do much about it. There's a woman in Montreal tonight, perhaps 70 years old, perhaps older, who remembers waking up on March 13th, 1989 in an apartment that had gone cold and dark in the night. She would have been in her 30s then, perhaps younger. She would have looked out a window at a city that was simply off. Not a neighborhood power cut, not a blown transformer on her block. The entire city, dark, as if someone had reached down and switched off the province. She may have lived through it without ever knowing that the cause was a cloud of solar plasma that left the sun 2 days earlier and traveled 150 million kilometers to arrive specifically and catastrophically at the intersection of Earth's magnetic field and Hydro-Québec's transmission infrastructure. She may not know that a cloud of similar velocity is arriving at that same magnetic field today. She may not have been warned. Most people have not been warned. The G3 watch is public. It is on NOAA's website. It has been reported. But the architecture of public emergency communication does not yet treat space weather the way it treats a hurricane bearing down on a coastline. There is no mandatory evacuation. There is no shelter-in-place alert on every phone in the storm's path. There is a number on a website, updated in near real time by scientists who understand exactly what it means. And that number does not currently translate into the kind of urgent, universal warning that the stakes may eventually require. The sun is approximately 4. 6 billion years old. It is currently in solar cycle 25, which reached its predicted solar maximum in the period around 2025 and 2026. Solar maximum is not a single day. It is an extended period of peak magnetic activity in which active regions form more frequently, achieve greater magnetic complexity, and produce more significant flares and CMEs than at solar minimum. The current period, June 2026, falls squarely within this active phase. Active region 445, which produced the X1, 0, M9, 3, and M7. 7 flares on June 3rd carried a beta gamma delta magnetic classification, the most energetically loaded configuration in the solar classification system. Active region 4456, still active as of the time of this writing, also carries that same beta gamma delta designation. The stage is not clearing between events. It is, in the most precise scientific sense of the term, still accumulating. What the long view perspective adds to this picture is a number that puts the human moment in its proper frame. In the 4.6 billion years of the sun's existence, the geomagnetic storms of 1859 and 1989 and May 2024, when an X8 7 flare drove a G5 storm with a DST of negative 412 nanoteslas, are not anomalies. They are the baseline. They are what a middle-aged G-type star in a quiet phase of the main sequence does at intervals that the geological record, in ice cores, in cosmogenic isotope deposits, in the layers of sediment that encode 10,000 years of solar weather, confirms are regular, recurring, and inevitable. The question of whether the sun will again produce a Carrington scale or near Carrington scale CME directed at Earth is not in dispute among solar physicists. The question is only when. And the system operating beneath the surface of every technological dependency of modern civilization, the grid, the network, the satellite constellation, was built in the decades since the Carrington event, without fully reckoning with the fact that the sun that bathed the construction of that system in warmth and light also periodically fires magnetized plasma clouds at it at speeds that dwarf anything human engineering has ever produced. The G3 watch for June 8, 2026 may pass without catastrophic consequence. The Biza may arrive northward. The magnetosphere may hold its shield closed. The lights may stay on. The GPS may remain accurate. The solar wind may dissipate, and the KP index may drift back below storm thresholds by June 9th or 10, as NOAA's forecast suggests. That is a real possibility, and it is worth naming directly. But the event unfolding today is not significant because of what it will definitely do. It is significant because of what it demonstrates about the state of the relationship between this star and this planet, a relationship that has been unfolding for 6 billion years, in which all of human civilization occupies the thinnest imaginable slice of time, and in which the infrastructure of that civilization has never once been tested against the conditions that this star is known, from the documented record, to be capable of producing. When the Hydro-Québec grid collapsed in 90 seconds on March 13, 1989, the sun had been doing this for 6 billion years. It had done it before the first human ever looked up and wondered what the bright thing in the sky was. It will do it again long after the last instrument we have ever built to measure it has gone dark. The cloud that left the sun on June 6, 2026, traveling at 1,400 kilometers per second, is not a warning in the metaphorical sense. It is a physical object. It has mass, it has velocity, it has a magnetic field. And it is arriving now.